call me.
Okay, okay. Sure, sir.
Okay, so recording has started. So Prathamesh, you can continue, and only at the end, maybe at 10, I'll check. But in case I'm not here and the recording is not stopping, then just let inform me.
Sure, sir. Sure, sir.
Also, students, if during the lecture, if you feel that the lecture, the recording is stopped or something, then just inform Prathamesh, or you can call me also, because I think everyone has my phone number, that the recording is stopped, because it is important to record all the lectures. Okay, so I'm stopping here. Prathamesh, you can continue from this point.
Yeah. Okay. Thank you, sir. So, is my voice audible to all?
Yes, sir.
Yes, sir.
Yeah. Okay. So, a very good morning to all of you. So, my name is Prathamesh Nitin Tanksale, and I'm a PhD student under Dr. Shirshendu sir, and I'm also currently the course TA for this course, right? So today we are going to look at the Hawkeye replacement policy, which you perhaps might be knowing that is one of the state of the art technique. So, so when we talk about Hawkeye, so what is the reason the authors choose to give this paper the name Hawkeye? So just out of curiosity, so I just found this pic in the internet. So the reason for Hawkeye is there has been many solutions for cache replacement policy, but the Belidy's optimal solution, which looks farthest into the future, right? That has not been implemented because it is impractical. As we know that the future is not known to us, right? So they try to somehow mimic that policy, looking at the past behavior, right? So let's dive deep into this. So a small caution or a small note that some of the images are directly taken from the Hawkeye 2016 ISCA paper, and all the relevant sources are belonging to the author itself. So for today's agenda, I would be looking at the background of the problem, the motivation for Hawkeye, working of Hawkeye, and experimental results. So we will cover all these topics in some detail. So looking at the background, so what is this everything all about? So there is a CPU, and we all know that the processor requests something, and if there are no caches, then the main memory is having long latency, right? So when there is long latency, this concept, the researchers try to evolve the hierarchy of caches. So when we talk about the entire hierarchy of caches, we are mostly the L1 cache is designed for a very quick response. That's the very small latency. But the LLC is designed keeping in view there are although many factors, but capacity is one of them. So what is this Belidy's algorithm which they are trying to mimic? So let's consider a set associative cache. In this figure, I have chosen a four-way and n set associative cache. So let's assume that there is this access pattern, right? So this access pattern, all these access patterns are mapping to set one. So let's see A, B, D, E. Initially the cache was empty. So all the blocks are entered into the cache. Now we are coming at point C, right? So now there is no space in cache for block C. So what we do? So we are trying to replace the block. Now what this Belidy's algorithm do is, it tries to look farthest into the future, right? So whichever block from current timestamp is far, which will be used farthest into the future, the Belidy's replacement algorithm will kick that block out and insert the incoming block, right? So when we look at the previous accesses, we find that the block D, right? So the block D is farthest used into the future. So from this cache set, we evict block D, right? Let me just take the pointer so that, is the pointer visible to all of you?
Yes, sir.
Yes, sir.
Yeah, okay, fine, thank you. So this block C will be placed instead of block D, right? So far so simple. Now let's look at what is the background of this. So as I have seen that you have already studied some of the recent replacement policies like LRU, BIP, DIP, SRRIP, right? So you know this, that exists policy that is very close to the Belidy's optimal. but the existing policies are built on heuristic, right? So they only cater to certain workloads, right? Just like we all know, LRU is recency friendly, right? SRRIP tries to deal. So we will delve more deep into this. So when in the actual system, the access patterns are quite complex, right? So to cater to this access patterns, we need some very sophisticated replacement policy. Now, as you all know, you might be knowing this slide, that the access patterns are recency friendly, right? So if you look at this pattern, that is A1, A2 to AK minus 1 and AK, and the same pattern is repeating for the n cycles, right? So it is very cache friendly in nature, right? So any policy like LRU might be giving good cache hits on this particular access pattern. Now if you look at the thrashing access pattern, perhaps you might be also familiar with this pattern, as the size of k is greater than the cache size, right? So the pattern is repeating, but the cache size is not sufficient to hold the pattern. So in this case, what will happen? Most of the policy, just like LRU, it will get at most almost zero or near to zero hits, right? So the people have developed some techniques which try to prevent, some subset of these blocks are prevented and get some hits, right? So we will be looking at this pattern. Then there is a streaming access pattern, right? So this access pattern is also quite popular because this pattern is the one which which degrades the performance of LRU very highly, because you put something in the least recently used position, and it takes a long most recently used position, and it takes a long time for it to get evicted, right? Now in today's multi-core era, we see that the mixed access patterns are very, very common, right? So there is a combination of any of these. So this makes the current state of the art techniques. So the Hawkeye paper was proposed in 2016, right? So all the techniques before 2016 were not able to handle this complex access pattern. So so this is the point. So I think this point we have already discussed, that the recency friendly policies such as LRU has its limitations. Then there is RRIP policy, right, which reduces the overhead also by using a re-reference interval prediction. And some of the thrash resistant policies are also there, which keep some block which is known as the active working set, right? Active working set in the cache, so that it can get at least some hits. So let's take a small example, which is also a motivating example for this paper. So let's look at this matrix multiplication code closely. So this is a standard matrix multiplication. This is matrix A, this is matrix B, and this is matrix C. So what we see is, in if we have to calculate this value C1, right? So how we can calculate this value C1? It will be this A1 into B1, then A2 into B2, right? So although this matrix multiplication problems looks to be very simple, but the each matrices are having different reuse behavior, right? So this matrix, let's compute this short term reuse. So why I'm calling this short term reuse is because this C1, if you have to access C1 again, it is very easy to access it directly, right? But during a casual matrix multiplication, when A1 is multiplied by B1 and so on and so forth, the after calculating this particular field, right, this B1 and B2 and B3 and B4 will take a long time, because then this second field will be computed, then third, then fourth, and then this, right? But this A1 will be used to compute each and every block, right? So this A1 is having medium term reuse. The elements in this matrix is having long term reuse, and the elements in this matrix are having short term reuse, right? And as we all know, this matrix multiplication is highly used in all of the optimization techniques and all. So nearly many of the current day processes are using this similar kind of code. So we want a cache replacement policy at last level cache which is sufficient to handle all the three, right? So there is a small comparison here in which we can see all the prior techniques, and this is the belly, right? This is the theoretical belly, and on the y-axis we can see the number of hits. So we can see only the theoretical belly can capture all the three effects, right? So the author of this paper tries to mimic this. So this is a standard triply nested loop for matrix multiplication, right? So C enjoys a short term reuse, A matrix enjoys a medium term reuse and B matrix enjoys a long term reuse. And the conclusion of this particular example is that the existing technique can't capture all, but we require some technique which somehow or other mocks the Bellidy's policy, right? Am I confusing you, or are you getting it?
It's fine, sir.
It's fine. Okay, thank you.
Yes.
Yeah. So now let's look at what Hawkeye tries to do, right? So basically what Hawkeye tries to do is it creates an algorithm, to track the history of the past memory accesses, right? So it builds upon the assumption that a past is a good representation of the future, right? So this is the basic assumption which Hawkeye builds upon. Then comes the important point. What Hawkeye does is it observes that the OPT, so from now on, this OPT will be the Bellidy's optimal solution, which will require future accesses, right? So this is impractical. So they observe that this, if a load instruction has historically brought in lines that will produce cache hits, right? So I request all of you to focus on this particular statement because this is a bedrock statement of the entire paper. So what they are doing is they are looking for a load lines. So this load means the processor loads, right? So a processor is requesting block A, right? So it will have its program counter, right? So it has historically brought in lines that will produce cache hits. So then in future, the same load instruction is likely going to bring in lines that will produce cache hits, right? So I think this point will be clear with the example we are looking for. So let's take a very small example. The example here is, let's take a small program which has this particular behavior, right? So this is the program value, this is the PC value, this is the instruction, and this is the memory block which it is accessing, right? So let's look at this particular PC value, right? So what it is doing, it is it is accessing the memory block B, right? It is a load instruction. So to predict whether the current loaded memory block B will be hit or miss, so this is their problem statement, right? Because all the existing replacement techniques, they are just looking at, memory accesses which are very small, but they are looking at the program counter behavior. So this is a add-on on which the paper is trying to build itself. So if they want to predict whether what will happen if the Bellidy's optimal policy would have been there on past, so what would have it be? Whether it would be a hit or a miss. So to know this, what they are doing is they are looking for the PC which access this block in the history, right? So assume that down the y-axis is the positive time, right? So currently this is the PC. So currently we are here, and in the past the same PC, this same PC, that is the 100, has accessed memory block A, right? And now the same PC is accessing memory block B. So the fate of B, right? So if we have to guess whether B will be hit or miss, it will depend upon what the same PC did to this memory block A. So this is how their assumption is played out. So what will happen is the prediction of B will depend on whether A was a hit or miss, right? So this is their basic understanding of how the entire history and the program counter and the prediction table is implemented, right? So just to summarize it again, the fate of this B, that is whether it would be hit or miss, if we have to determine it on runtime, so we will look at the PC, that is the 100 PC, we will look into the history whether this PC has another block A, and what was A in past, was it hit or miss. So if it was a hit, then B would also be hit. So this is the kind of prediction which we are looking at. So to begin with, there are two components, right? So the first is to reconstruct the Bellidy's optimal solution from past cache access, right? So this we just now we just try to build it with the intuition, right? But we have to come up with a sophisticated algorithm to build the past memory accesses, right? And the second is that how to make sure that the predictor learns this behavior, right? And then the predictor informs the eviction decision, right? So for the future loads, so these 2 points we have to see how this pans out. So let's look at the problem. So the problem is the OPT solution, right? The theoretical OPT solution requires a long view into the future, right? The view of the future is very high, right? So what does it mean is, let's say our cache capacity is like 2 MB, right? So on the x-axis you can see 1x, 2x, 4x, that is times the cache capacity. So if the cache capacity is 2 MB, an ideal an ideal optimal solution, which is just theoretical, would require at least 16 times the accesses of the future, right? It should at least know 16 times the accesses of the future. So if a cache capacity is 2 MB, at least 32 MB of future accesses should be known, right? So we don't even know one future access, right? But what is the assumption? The assumption is whatever happens in the past, there is very highly likely that happens into the future. So if we have to mimic the Beladi's algorithm in future, what we have to do is we have to at least store 8x or 16x history of the past accesses to the cache. So if we are able to store 8x history of the past, right? So we can come up with an algorithm which mimics the past and tries to predict the future. So this is the problem. This requires a lot of overhead, right? So we will look how this paper you know tries to come up with some effective solutions and optimization strategy to minimize this. And on the y-axis we can see the error compared to the infinite opt, right? So this infinite opt is the theoretical. So the minimum the error, the better it is, right? So melodies look too far into the future. So this is the problem. So the problem is we have to remember a long history of events. So they introduce two intervals. So this is an example we will be looking into. So they look at two intervals, right? So they look at the usage interval and the liveness interval. Now, what do we mean by usage interval, right? So usage interval is the interval of a block when that block was accessed in the past and at what time that block will be accessed in the present, right? So let's see that the time is moving in this direction. So this x bar what we are seeing is the present, right? So when this x came into the past, this is x. So the difference of this timing is the usage interval. You got it, right? So the difference in the timing is the usage interval. And what is the liveness interval? The liveness interval is, if I will give you the definitions in the next slides, but the point is the liveness interval is the time the block will be there in the cache unless and until the OPT policy will evict it, right? So for the A, the liveness interval is this 1 unit. For B, the liveness interval is 1 unit. For C, the liveness interval is 1 unit, right? So this is just a small example, but just to clarify it again, liveness interval is the time for which the block will be there into the cache when the OPT policy is there, right? And the usage interval is when this block came in the past, right? So the difference between two. So let's look at liveness interval. What does liveness interval brings on the table, right? What are the advantages? So the advantages of liveness interval is it gives us information about the reuse distance, right? So for example, if we can see the liveness interval of A is just 1 unit, so it gives us reuse distance, right? So A will be just coming after one access. So this is the reuse distance. And this point is one of the most important point which gives us the demand on the cache, right? What is the demand on the cache? So just to explain this point, we will come to one figure, right? So I will explain into the coming slides. And the knowledge of both of these policies is required, right? So prior to 2016, as far as my knowledge is concerned, the first point was very efficiently utilized, right? So there were many replacement policies which were using this reuse distance predictor in some way or other. They were trying to do this, but this demand on the cache is very new concept. Just to give you a small example, what the demand means, right? So let's assume that the cache capacity is only 2 blocks, right? So cache line 1, line and blocks can be used interchangeably. So the cache capacity is just 2 blocks, right? So what do we mean by demand on the cache? So this x, right? So x and x dash, the liveness interval seems to be very long, right? Compared to the cache capacity of 2. So all the previous techniques, what they will do is they will think, oh, the cache capacity is 2 and the usage interval of x is, let's say, 6. That means that, oh, there is no chance that the x is having a chance to get hit in the cache, right? But this logic is false, because you see the demand on the cache is very less, because A and A, it will be there, B and B will be there, C and C will be there, right? So there is, even if the X is having high usage interval, it can get cache hits. So the demand is also very important. So I think this point will be much more made much more clear in the future slides. So the knowledge of both is required for, good replacement eviction decisions. So let's, look at the bird's eye view of Hawkeye. So what is a Hawkeye? So basically what Hawkeye tries to do is tries to, classify it as a, sorry, it tries to make it as a binary classification problem, right? So whatever is the incoming block, which is the current incoming block, it tries to classify whether the incoming block is a cache friendly block or a cache averse block, right? So cache friendly means there is good chance that it can be used again, and cache averse means that there are very less chances that the block can be reused again. So just evict the cache averse block, right? So it is a kind of binary classification problem. Now the cache friendly lines are inserted with high priority, right? So this is the logic. And while cache aware lines are marked as eviction candidates for future conflicts. So I think this is pretty much basics, right? So whatever is the cache friendly, try to give it high priority so that in future that particular cache blocks might get hit. And whatever cache averse lines are there, just make sure they are the eviction candidates, and in the near future just evict them, because they are unnecessarily utilizing your precious cache memory, so that it can be given to some other high priority blocks which can get cache hits, right? So any questions till now? Okay. So if you have no questions, can you give me some thumbs up that are you able to understand it? Should I slow down my pace a bit, or is it okay?
It's okay, sir.
Yeah.
It's okay,
Okay.
sir.
Okay. Thank you. So let's look at the structure of the Hawkeye, right? So the Hawkeye has basically three components. It has a predictor, right, which we saw, the PC based predictor, which makes the eviction decisions. And then there is a humongous task, that is we need to simulate this OPT gen, right? How to simulate the past behavior so that in the present time we can take some decisions which are, very much similar to the theoretical ability, right? So this is a humongous task, how to produce this OPT gen, right? And then even if we are able to produce it, we are maintaining 8 times the history of the past accesses, right? So that is too much. For a 2 MB cache, we need to make 16, we need to remember 16 MB of previous accesses. So how to come up with an optimization technique, right? So how it uses sampler to reduce the state. So we'll look into this. So this is, the block, we can say the flow chart kind of thing of this prediction, right? So let's look at in bits and pieces. So this is the training period, right? So first we will look at the training period. So there is an incoming PC. What will happen in the training period is the address will be looked into the history, right? And it takes something like OPT gen, or which is known as occupancy vector, which I will explain in the next slides with very good animation, so that each and every step what is happening you might be able to particularly know about it. So the basic criteria here is the address is sent to the OPT gen. It predicts whether it is a hit or a miss, right? So it just predicts whether it is a hit or a miss. And then there is this PC based classifier which is provided here, right? And then it predicts, looking at to the counter values, whether we should give this cache value good RRIP or not, right? And then the prediction. So first the training, then the prediction, right? So we will look into this, right? So the OPT gen. So what OPT gen determines is whether, if the OPT policy was used, whether the cache will get hit or not, right? And this is I would again request all of you to please give specific attention to this particular statement. So what OPT does is it repeatedly asks these questions again and again. So what is the question? The question is, given a history of memory references, right? That includes a reference to a cache line X, right? Which we saw in the figure. Would the next reference to the same line, which referred to as X dash, will be a cache mid or hiss, right? So repeatedly it goes and asks this question, whether it will be a hit or miss. As soon as it finds there is a past access to that particular incoming block, it repeatedly goes there and finds the question, asks these questions, right? So the basic definitions are like the usage interval, right? Whenever it comes to the next time, the liveness interval is the cache line's liveness interval to be the time period during which the line resides in the cache under OPT policy, right? So generally it's two of them are slightly confusing when we are reading at the beginning, right? But just to make things clear, this is the block's next access time and this is the block's time in the cache unless and until the OPC policy will evict it, right? So this is the difference, right? And at any point of time it will right. So this is again one more important point. So when we are looking at the pressure on the cache, right? So we were looking at this particular point, what is the pressure on the cache? So at any point of time, if the usage interval, the number of overlapping liveness interval matches the cache capacity, right, that the X would be hit. So let's dig more into this, right? What is this overlapping problem? So let's look at this overlapping problem, right? And then it uses the occupancy vector. So, so let's look at this problem. This is a sample access pattern. So this, so what the authors of this papers have did is they converted this problem, right? So they converted this caching problem into an overlapping problem, right? So many of us in the data structures, right, we have seen this problem which is known as the overlapping subproblem of the lines, right? So what is the overlapping subproblem? Let's say that this was the access sequence, right? And the cache capacity is 2. So what will happen is this A will come, right? And when the A will come into the next time, this is at this point, we just, make the line. So A first came at time t equal to 0 and then it came at time t equal to 6, right? So we just connect these two lines, right? So what the algorithm says is, what is the concept of, this overlapping lines, that if the cache capacity is 2, right? So that at any point of time, there should not be two overlapping sublines, right? So then that makes that the solution is OPT. So this is the solution. So this is the incoming access pattern, and the green bar explains that these particular lines are cached, and the red bar explains this particular cache lines are not cached, right? So for the time being, we will not discuss why these two particular lines are not cached. In the next slides, I will be explaining why these are not cached. But the overall concept is that at any point of time, just take point t equal to 5, right? So at t equal to point, go to y-axis, right? Only two lines, maximum two lines should be there. So this A line is there and D line is there, right? At any point you can say at t equal to 7 if you see, right? So this line D is there and line F is there, right? So at any point of time, maximum only two lines will be there for overlapping because the cache capacity assumes is to be 2, right? If there is a 16-way set associative cache, then at any point of time in the history, there should not be 16 overlapping lines, right? Because if there are more than 16 overlapping lines, even the OPT solution will not be able to get you hit, right? So this is the way. So let's try to recreate, right? So again, I would like to draw your attention to this particular diagram, as this will be the crux of the the OPT gen algorithm, how they use this, right? So let's assume the same access pattern again, that is the access pattern which we saw into figure, and this particular field is the timestamps, right? The time at which this arrived. So when the A will arrive here, right? So the time is moving in this direction, just to make sure. Increasing amount of values means we are in the more present, right? So when the pointer will come to this, right? When A will come for the second time, right? It will look when was the time when A came previously, right? When any block will come for the first time, there is nothing to do, right? But when it will come for the second time, we will get its usage interval, right? Oh, so usage interval of A would be 6, right? So let's try to recreate this. So let's see what happens at time t equal to 0, right? So a comes, right? So this is the occupancy vector entry which we are entering, right? So by this we will recreate the Belady's algorithm, right? So whenever the block comes for the first time, we just insert here 0, right? So at time t equal to 1, now b will come. Now b is also there for the first time, right? So we again insert 0 here. So what happens at time t equal to 2, right? Now the B is coming for second time, right? So now B will be a hit. You got it? So this entry of 0, so this B, as you can see, this B is coming for the second time. Now we can calculate the usage interval, right? So what is the usage interval? That is 2 minus 1, right? That is 1. So any blocks which are present between this B, we will increment that by 1, right? Right, just make sure, remember that we are trying to recreate that overlapping problems, right? So now that this b to b line is joined, just to go back some here, right? So this is time t equal to time t equal to 2, right? T equal to 2. So this, now this b to b line will be joined, right? Otherwise it would not have been joined, right? So this is time t equal to 2 and b is already there, and then we increment all the blocks between this by value 1. Now there is only one block, so increment it by 1, right? And the cache capacity is still less than 2, right? We assume that the cache capacity is 2, so there will be only one overlapping, so this is allowed. So what OPT will do is, okay, so now as there is only one overlapping and the cache capacity is 2, we will allow this line to get hit, right? So this is what they will do, right? Now what will happen at time t equal to 3, right? T equal to 3, C will come. C is also coming for the first time, right? So we will insert value 0. At time t equal to 4, D is also coming for the first time. So we will again insert value 0, right? At t equal to 5, E is also coming at the first time. So we will insert with value 0, right? Now this is very interesting. See again. So A is coming at time t equal to 6, right? So we will look into the past whether A was there or not. So now we find yes, A was there. So the usage interval of A is entirely from this block to this block, right? Then we see whether A can be there or not. So A will be there, right? So all the blocks, right? All the blocks from here to here, their value will be incremented by 1, right? You got this point? Any questions till now? You can you please provide me some feedback whether you understood this point, that whenever the next block will come for the next time, so the entire blocks in this usage interval will be incremented by 1.
Yes, sir.
Yeah. Okay. Thank you. So this is the trick. So this is how the dotted lines are connected, right? So this is how in the previous example we see the dotted lines are connected. Now let's see what happens at time t equal to 7. The f is coming for the first time, right? So again we insert it with 0. Yeah. So now you can see, right? Now block D is coming. So now block D will be inserted in this space, right? And now when was the time when D came? It was at time t equal to 4, right? So all the blocks between the usage interval 4 to 8, their values are incremented, right? So this 1 becomes 2, this 1 becomes 2, this 0 becomes 1, this 0 becomes 1. And still this cache capacity is 2, right? So still it is manageable, right? So who can tell me what happens at E? At time t equal to 9, what will happen?
So from the fifth point, the values will be increased by one.
Right, but if you increase this value by 1, so what will be this value?
So three.
3, but the cache capacity we are assuming is 2, right, for this example?
Yes, sir.
So this is what they will do. So when we are looking at E, we will look at this axis from 5 to 9, right? But what will happen is this block will be incremented to 3, right? But the cache capacity is 2. So see, the important point is this is the history, right? So whenever the block will come, This is the current block. When I am saying at time t equal to 9 means this is the current time, and at this time we have to take decision, right? So this is the current time, we are standing here, right? The OPT gen is standing here, right? It sees E, it sees E. So when it sees E, it has to take a decision, right? Which are, what RRPV values should I give it, right? It is a cache, is it a cache friendly line or is it a cache averse line, right? So for that, it looks at this OPT gen, and when it looks, oh, this came at time t equal to 5, and when it looks to increment this block, it sees that the block is already at time t equal to 2, right? This means that even if the optimal policy was used, right, even if we were having knowledge of future, it is impossible to get hit for this cache, right? So this is the cache capacity problem, right? We look at this capacity misses and all, right? So the capacity miss means what? So this E is a capacity miss, which means even if we are having the theoretically best policy which is able to see future, still we will not be able to get hit because the cache size is less, and already two blocks are there which are getting hit, right? You understood this point? So this will not do anything. So that's why I've marked this in red, right? So this will be a miss. So this, all this green were hit, right? So this B was hit, this A was hit, E was hit, and the A was also hit, right? So this is how we work. Then what happens at time t equal to 10? F will come. Again we will insert with 0. When was the last time when F came? It was at t equal to 7, right? So this was 1 0 0, and we will increment it, it is less than 2, so it will be incremented to 2, 0 will be 1, and this 0 will be 1, right? So again, can any one of you tell me what will happen at time t equal to 11 when C will come?
So from 3, everything would be incremented by 1.
Right. So, but then it will be a cache hit or a miss.
It will be a hit because C's value would be 2.
No. Yeah, Upasana, I think you have capacity miss, right? See, because see what will happen is you get it, Rohit?
Oh, got it, sir. Yeah.
Yeah. So this value is 2, right? From C to this C, if we are incrementing everything, then this value is already 2, right?
Yes, yes, yes.
Yeah, so this will again be a capacity miss, right? So this is the thing. I will share slides with you also, so that you know you will be able to do this animation again, right? So this is the point. So when this C will come, this point has to be again 2, right? So this is the way. So now you know, let's try to reduce the size, right? Because for every cache way we have to store this, right? So they use the concept of time quantum, right? So what is the concept of time quantum? The time quantum means whenever there is an access to cache set, right? So when A will come to the same set, time is 0. When B will come, the time is 1. When this B will come, the time is 2, right? But this is a very slow and tidy process. So what they have assumed is they have come up with a concept known as time quantum, in which they will only check cache at every 4 accesses, right? So when A, B, B, C, D will come, right? So after every 4 access they will check, just to expedite the process, just to make it fast, right? And I guess you are more comfortable with this term, that is set dueling. You have, I think, heard this in the DRRIP paper also, right? What the set dueling does is it tries to, you know, take some sample sets and try to mimic it, right? So what is a sample cache? So they use a sample cache, you know, just to reduce the overhead, right? Let's say there are 2048 sets in a cache, so they are sampling just 64 sets, and they are looking at all these experiments which we do. They are just looking at the 64 sets, right? So there is an underlying assumption that that particular 64 set is well enough to represent the entire cache, right? So they use this byte address and load PC, you know, just to recreate this, right? So now what they're doing is they're reducing the overhead by this way, right? They are reducing the overhead in this way. So what is the Hawkeye predictor, right? So this we have already seen there. So what is the value? Now the predictor guides the insertion and eviction decisions. It tracks the last PC, right? And it is the one which classifies whether a line is cache friendly or cache averse, right? This is the table, right, which we are looking at. So a PC will be indexed here, and we will be looking at this, right? So let's look at the, you know, what is the PC bias. PC bias means now what is the chances that looking at the PC we will get whether this is a hit or a miss, right? So they get nearly 90% of the time. You see, on average, not 90, if you can say it is nearly 88 or 89. On average, on 88% they say they get whether it is a OPT hit or a miss, right? Cache averse, right? So this is one more important point, that looking at the OPT gen, they will determine whether a line X would be a cache hit under a OPT policy or whether it will be a cache miss, right? So based on this, they will look, and the most important point is they will train the predictor positively and negatively depending upon what was the last PC accessed, right? So what do I mean by this is, so let's look at this example, right? So let's say, because all these three are different PCs and they are all accessing memory block A, right? Now let's say we are currently at this particular instruction, right? Let's say we are at instruction number 3. Now we are instruction number 3. Here is the point which we are taking decision, right? So if we get a hit to this particular block A, right? What does that mean? It means that all this previous PC which brought this block A into the cache and we are getting hit, they are useful, right? So they will increment the counter corresponding to this value. So this is what they meant. Whenever a block is getting hit, if it is getting hit, then we will look at the previous PC which brought this block and we will increment their counters. And if A is a miss, then A was brought by these two PCs, right? So we will decrement. We will say it is like giving some confidence. It is like, oh no, these PCs are not that good. They are giving some wrong values, because if they were giving good values, it would have been a hit, right? So it's like training positively. It's like giving a reward, right? So this is the way. So 90% of the times they are able to get it, right? And the predictor has 8,000 entries. It is using a 3-bit counter for training, right? So 3-bit counter means value 0 to 7. So any value which is greater than 4, they consider it as cache friendly, and the counter value is less than 4, they consider it as a cache averse line, right? So what is the cache replacement thing, right? So what is the key difference from the simple RRIP policy which we have assumed? So the difference is that if it is a cache averse line and it is a cache hit, right? So what we will do is, in the interest of time, we will just cover up to this particular slides and then we will be opening to questions, right? Then next, I think we can cover in the tutorial class. So the point is, if the line is a cache averse line and the point is it is getting a cache hit, right? So what does that mean? Even if this line is not that good, but still it is getting cache hit. So what will happen in an ordinary RRIP? It will be inserted to 0, right? If it was an ordinary RRIP, they doesn't discriminate whether a line is cache friendly or cache averse, right? If it is getting hit, then this RRIP value is decremented. And by the way, again, so we are using 3-bit counter, so it's 0 to 7. RRIP value of 7 means it is very close to eviction, right? So RRIP value 0 means it is a cache friendly thing, and RRIP value 7 means it is very near to eviction, right? And on a cache averse line, if it is a miss, then the RRP value is 7, right? Now cache friendly block, then cache hit, obviously if there is a cache hit and the block, the predictor is saying it is cache friendly, obviously it is RRIP equal to 0, right? So this we all know, this is a hit promotion policy of RRIP, right? But can any one of you explain what does this mean? The line is a cache friendly and the line is still a cache miss. Still it is giving RRPV equal to 0. What do you think would be the advantage of this point, right? This you all understand, that if it is a hit, then we give the value 0. But if it is a miss, in normal RRPV, what will happen? They will increment all the RRPV counters and look for the maximum line, right? What do you think would be the advantage of this? Anyone? Even on a miss? Anyone? Any answers? Just a random guess might also work. There is no compulsion that the answer must be right. Right? You got the question right, or should I rephrase it again? Can you provide me some feedback whether you got what I'm asking?
Can you please repeat?
Yeah, okay. So the point is, Dr. Shishendu has covered this RRIP policy, right? Yes, okay. Thank you, Basna. So what happens in this RRIP policy is whenever there is a cache miss, right? So whenever there is a cache miss, what will happen? It will look for maximum RRPV, right? For victim, right? When there is a limited space in the cache and cache is already full and a new block is to be inserted, right? And there is no space, so we have to evict something, right? So we have to evict a victim, so we have to choose some block to eviction, right? So what I am my question is, when the simple RRPV technique is choosing some block for eviction, right? And if there is no block, then the RRPV value of 7 needs to be evicted, right? But if there is no RRPV value of 7, they age all the lines, right? They increase the RRPV of all the lines and continuously check which is having maximum line, right? So if somehow the RRPV is 6, so this 6 will be incremented to 7 and then the 7 will be evicted. But in this, the Hawkeye is saying if the line is cache friendly, even on a cache miss, right? If it is a cache friendly line and even on a cache miss, the RRPV value is still 0. Ultimately, what happens? If there is a cache miss, then the block should be evicted, right? But it is still giving RRPV 0. So what might be the reason for this? Anyone? Just a random guess might be. There is no nothing such as, am I going too fast? Okay, Upasna, maybe due to capacity misses. Uh, Maybe due to the capacity it's miss. Uh, okay, you can look into that angle also. But the problem here is what they are trying to address is that when the RRIP value is, when the predictor is confidently saying that the line is cache friendly, right? So it doesn't matter whether the RRIP value is agreeing with it or not. What they are doing is they are still keeping it RRIP equal to 0. So that is the faith which they are having in their predictor, right? But what will happen is after doing this, they will age all the lines with RRPV value 6 just by 1, right? So as a kind of negative feedback that okay, for once I will keep RRIP 0 and age all the lines, right? So this is their presumption, right? And then they will detrain the predictor also, right? The predictor has been detrained, but the effect is not seen in the policy. So much more details are given in the paper. I think we can look into the paper also, right? So right, so this is the difference. The lines that are predicted to be cache friendly are always assigned an RRPV value of 0, regardless of whether they were hits or misses, right? So whether it was a hit or a miss, it doesn't matter. The RRPV value is equal to 0. So this is the concept. So this is where they differ from the simple RRIP technique. On a hit also it is 0, on a miss also it is 0. But on a miss they do some more things also, right? Right? And cache hits are promoted to an RRIP value of 0 only if they are predicted to be cache friendly. Now this is also one more difference. What is the difference? On a cache miss, the RRP value is 7. This we can agree, right? But on a cache hours line, if it is a hit, what will simple RRPV do? It will reduce this 7 to 0. But here the 7 is 7 itself. Why? Because they are saying that the predictor has says it is not a good line, so why to give it good RRPV value? So that is their basic presumption, right? So I think we will stop here because experimental evaluation it will again take much more time. So today is our tutorial class, right? When is it? Can anyone provide some insight? In the evening, it's it there, right?
6 p.m.
Okay, 6 p.m. So today 6 p.m. we will continue on from this, right? So I'm just stopping the presentation. If any one of you have any questions, perhaps some kind of discussion, just a second. So yeah, so perhaps we can take some questions then. If you have any questions, if on this slide maybe or
Prathamesh, you can share the slides now only. So maybe in the evening lecture, they will just cross check this and they'll come again. And you can also post the Hawkeye paper in Google Classroom after the class.
yeah, okay, sure, sir.
Okay. So I think the people are not updated with RRIP. So it's unfortunate because the course load is not much, but at least I'm expecting that all people who are here in this course are all mature, right? I should not pressurize you like the BTech students. I'm also taking a BTech course this time, and there I am taking regular classes, quizzes, and all. Why? Because I'm pressuring them to learn. But I think here you have chosen elective according to your wish, right? So it is your responsibility to means maintaining or keep updating yourself what is going on in this course. So I can see most of the questions are from Upasana, which actually you maybe not know, but Prathamesh and Upasana are batchmate. So I was expecting some more question from other people also. So next time you please prepare, and this from this week there will be a class test also, and in class test I will cover whatever I have discussed before this Hawkeye. So class test will be announced very shortly, and your first assignment will be also announced this week. And this announcement there will be less coding, but at least you should know a simulator called GemSim, how GemSim works. So me and Prathamesh will discuss, and Prathamesh will take a quick session on how to start with GemSim, and you need a Ubuntu machine, of course, for it. And then remaining he will explain, and then you have to complete your assignment by next week. So this week, today is Monday, and we'll give you another week. And yes, your class test will be in this week only. Okay, Prathamesh,
Yes, sir.
कितना टाइम लगेगा अभी सेकंड हाफ में?
सेकेंड हाफ में सर अभी 20-25 मिनट्स बस.
ओके. सो जो चैलेंजेस फेस करते हैं ना हम लोग चैमसिम में, वो भी थोड़ा सा शॉर्ट में बता देना कि जो चैमसिम किस एंगल में बेटर है और कब चैमसिम जो है प्रॉब्लम क्रिएट करता है, वो भी थोड़ा
ओके
थोड़ा एक्सप्लेन कर देना इन शॉर्ट, ज़्यादा डिटेल में नहीं चाहिए.
ओके ओके ओके.
ओके. और
हाँ.
इसके बाद वही अगर तुम्हें टाइम मिलता है तो अगर देखो, अगर तुम्हें लगता है 30 मिनट्स में खत्म हो जाएगा, तो फिर 30 मिनट्स टाइम है, उसमें तुम इन शॉर्ट में चैम सिम के बारे में थोड़ा भी बता दो कि कहाँ से डाउनलोड हो सकता है, तो दोनों काम एक साथ हो जाएगा.
ओके ओके ठीक है, आई विल डू दैट
तो
सर.
इसको थोड़ा ऐसे करो कि एक्सपेरिमेंटल एनालिसिस तो इतना डिटेल में डिस्कस करने की जरूरत नहीं है, मैं हालांकि करता भी नहीं हूँ. ओके.
ओके ओके.
तो थोड़ा डिस्कस करके इसको यहाँ पे खत्म कर देना, और उसके बाद चैम सिम के थोड़ा प्रिपेयर कर लेना कि मतलब इंस्टॉल कैसे करे, और जो बेसिक, ताकि वो यहाँ से स्टार्ट कर पाए चैम सिम. वो लोग इंस्टॉलेशन एटलीस्ट 1-2 दिन में हो जाए, उसके बाद हम असाइनमेंट अपलोड कर देंगे.
ओके ओके श्योर सर श्योर सर.
ओके.
ओके.
ओके, देन आई एम स्टॉपिंग द रिकॉर्डिंग हियर, एंड maybe you can also, Prathamesh class is done, right? They can leave.
Yeah, 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 yeah. Class is done, sir. Yeah. If
Okay.
they have